Exercise time. So 3-point charges lie along the x-axis as shown in below diagram. Calculate the magnitude and direction of total electrostatic force. Yesterday we were talking about electric field. Now we are back with electric force. Now I hope you still remember the steps, the 4 steps, right? Dotted line, so we already have that here. Number 2 is to find out the direction. So what is the question asking? It's asking about the force exerted on Q1. So how does Q1 feel about Q2 and Q3? So Q1 looks at Q2. Oh, we have different charges. I am attracted to this person. So this guy is F on 1 by 2. And how does Q1 feel about Q3? Q1 has the same charge as Q3, so Q1 is saying that Q3 is not his type. Okay, so he is going to repel Q3 by going the other way. So this guy is F on 1 by 3. So if I were to write this in an equation to find out the resultant force on Q1, my equation would be F1 vector equals to F13 vector plus F12 vector. Okay, this is the direction. Now the next step is to find out the magnitude. So F13 is equal to KQ1 Q3 over the distance between charge 1 to charge 3, which is 12 plus 20, right? Both, I mean, you have to calculate from Q1 to Q3. So it is 32 centimeter, which is 0.32 meter. You have to convert this to SI units. Okay, so that is 0.32 squared. And what about F12? KQ1 Q2, the distance between charge 1 to charge 2 is 12 centimeter. That is 0.12 meter. So 0.12 meter squared. 0.12 meter squared. Okay, so to write down the equation betul-betul, let's write the Q1 charge here. So this is F12, this is F13. They are both on the x-axis. There's no angles. Okay, so now we can padam this guy over here. Whoa, bersabar. Okay, alright, so now I want to put in my equation. So this is, alamak, I forgot what are the charges. Come back. Okay, let me put it somewhere else. Okay, just put it there. Okay, so the charge is 9 times 10 to the 9. Q1 is 12 micro. Micro is 10 times 10 to the minus 6. Sorry, it's 10 to the minus 6. That's a micro. And divided by 0. What is the charge Q3? Q3 is 36 times 10 to the minus 6. The distance is 0.32. We already decided that. And this guy is 9 times 10 to the 9. What is Q1? Q1 is 12 microcoulomb. 12 times 10 to the minus 6. What is charge 2? It is 20 times 10 to the minus 6 over the distance between charge 1 and charge 2, which is 0.12 squared. We have decided that. And using my trusty calculator, the answer would be... Okay, so I found out that F13 is 150 Newton and F12 is 37.97. Now, since these forces are acting on the same axis, do I have to resolve it? The answer is no. I can just immediately solve it. So I need to know if I already know the magnitude, right? And I know the direction, so now I have to put in the direction here. I don't have a table because they are on the same axis. So 150 is this is F13, it is going to the left. that's a negative. F12 is going to the right, so it is a positive. So to answer this equation, so F1 vector is equal to 150 plus 37.97, and that is 112.03 negative Newton. The negative sign means that the resultant force acting on this charge Q1 is to the left. Now, if I were to draw that, if I were to label the resultant force on this charge Q1, the resultant force is this way. What is the direction? The direction is to the left. Is there any angle associated with resultant force? No, the angle is 0, but to the left. Okay. Next example. So 2-point charges Q1 minus 2 nanocoulomb and Q2 3 nanocoulomb are placed 3 cm apart as shown below. Okay. Determine the magnitude and direction of the resultant electric field strength at point M. I don't know why they like to use M. If it was me, I would use N because Nadia, right? Okay, so he wants to know what is the electric field acting at point M. Now remember, for electric fields, what do we have to do? We have to place a test charge at that point. So instead of placing M with N, put a test charge. That is more beneficial. So a test charge is placed. The test charge has negligible value. We are just using it to calculate for the electric field. So what is the direction? First is test charge. The first one is dotted lines, right? Oh, sorry, test charge. Test charge, dotted lines, force, 2 dotted lines. We already have that, thank God. Okay, and number 3 is direction. 4 is magnitude. Number 5 is resultant. Okay, so for electric field, you have the extra step, which is putting a test charge at the point of interest. So to solve for force, there was 4 steps. There were 4 steps for electric field. You have 5, which is placing a test charge. Very, very important. Okay, so now the dotted lines are there. Next step is to find the direction. How does the test charge feel about Q1 and Q2? So a test charge is always positive, and when it sees Q1, oh, they have different charges, I am attracted, and for the Q2 they have the same charge, I am disgusted, or I'm going to repel myself away from this Q2, far away. Okay, so the direction is found. So E2, this is the electric field exerted by Q2, and this is the electric field exerted by Q1. Okay, now we know the direction. Now let's find out the magnitude. The magnitude for E1. Where should I write this? Next one is finding out the magnitude. So let's find out for E1. E1 is KQ1. E1 is equal to KQ1 over the distance between charge 1 to point M. And how do I find this? Using Pythagoras theorem, I will find out that this is 5 cm. I think, let me try. 4 squared plus 3 squared, square root the whole thing will give me 5. Okay, so the distance between Q1 and point M is 5 cm, so this will give me 0.05 squared, and Q1 is minus 2 nanocoulomb. Remember, your equation only tells you the magnitude, it does not give you the direction. The direction is when you draw the diagram, right? So this is 2 times 10 to the minus 9. Okay, so and then for E2, the electric field exerted by charge 2 at point M. K, the charge is 3 times 10 to the minus 9 is a nanocoulomb, and then the distance is 4, so that is a 0.6 0.04 squared. Okay, so using my calculator, I will find out that the answer is, let me use magic. Okay, so I found out that E1 is equal to 7,200 nano per coulomb, and E2 is 1,608.75 Newton per coulomb, so Newton per coulomb. Okay, and then I want to know what is the X component and what is the Y component. But before I can solve for that, I need to know the angle, right? So now we go back to the diagram. For E2, I know that it is along the x-axis, so basically it's just an X component, and the Y component should be a 0. So that is for E2. So E2 has a 0 value for the Y component and something for the X component, whereas E1 has an angle with respect to the x-axis, and it should have an X component and a Y component. The X component should be this way, and the Y component should be going upwards. Okay, so that is the EX and EY for E1. Okay, so EY should be positive. Oops, sorry. E1 should be positive and EX should be negative. Tulis dulu kat sini. And the EX for E2 should be a positive. Okay, so let me rub this off and put it nicely. Kejap. Okay, so let's figure out the angle for E1. So the angle with respect to the x-axis is 3 opposite over adjacent. Tangent theta is equal to 3 centimeter over 4 centimeter, or opposite over adjacent. And centimeter cancels out with centimeter, so you get 3 over 4. Inverse tangent of 3 over 4 gives you theta. Okay, 3 over 4 gives you theta. So 3 divided by 4, and then you inverse that, you get 36.87. So 36.87 degrees. Okay, so now that we have the angle, what have we learned so far? So I know the magnitude for E1, I know the magnitude for E2. I have the directions in the diagram. E1 goes this way, E2 goes to the right on the x-axis, which means that E2 only has an X component and no Y component. E1 has an angle with respect to the x-axis, and it should have a Y component that is going upwards and an X component that is going to the left. And the angle that we have found is 36.87. To resolve your vector, so here you have to, so here the equation is related to cosine theta and EY is related to sine theta. Okay, so E1 cosine theta, and this guy is E1 sine theta, and we know what the theta is. It's 36.87, so I'm going to write that 36.87. Okay, and 36.87. So this would give you the magnitude. So 7,200 times with a cosine 36.87. Answer minus 5760 and positive 4320 for the Y component. For E2, we know that the EY is a 0, which means that we only have the E2 in the X, and this should be 16875. And then I'm going to add these two together to find out what is the electric field at point M. The X component is the summation of minus 5760 plus with 16875. That would give me, it would give me positive 1115. Keberapa dah? Kejap. And this guy is positive 4320. So nano coulomb. And this is nano coulomb. We know this is a positive value, which indicates that the X component of the resultant electric field is to the right, and the Y component of the resultant electric field is going upwards. The next step is to find the magnitude and also the direction of the resultant. Okay, kejap. my EM should be located in this quadrant because I have an X component to the right and Y component to upwards. So my resultant should be here. Okay, so this is just like guessing first. So EM, the magnitude is given by EX squared plus EY squared. Square root that. The answer is, and then for the theta or the direction with respect to the x-axis is given by the inverse tangent of EY over EX. And the answer is, let me write that down kejap. Okay, so using my calculator, I plugged in EX as 1115, my EY as 4320, square that, square root the whole thing, I will get 11925 Newton per Coulomb. So that is the magnitude of EM. So this gives me the magnitude. And the direction is given by inverse tangent of EY over EX. This theta is with respect to the x-axis. So if I were to label EM's theta, it would be over here. Okay, so this is how we get the magnitude. I'm sure you know this already. This is how we get the direction or the angle for our resultant electric field. Okay, I hope that helps. So if my question asks you, what is the direction of the electric field at point M? Your answer would be the direction is 21.24 degrees above the x-axis. Okay, so to know whether it is above the x-axis or below the x-axis, you need to draw this diagram first, right? You need to know your EX and your EY. If your EY is positive, go up here. If your EX is positive, to the right. And your resultant will, your EM will always be in between the EY and the EX. Always in between the EX component and the EY component. Okay? Alright. Okay, so now we go into electric field lines. So the electric field lines were introduced by Michael Faraday. It is a convenient aid for visualizing electric field patterns around a system of charges. Now, is it important to visualize these electric field lines? The answer is yes, because you will be using this to calculate for electric flux. What on earth is electric flux is coming your way, so be patient. Alright, so electric field lines, you need to know how to draw it. So basically, for a positive source charge, the lines will radiate outward, and for a negative source charge, the lines will point inwards. And I told you there's a trick to you don't have to memorize. There's a trick to this. So my trick is put in a test charge over here, a teeny weeny test charge. How does the test charge feel about this charge? How does this test charge feel? Kejap, dia tengah auto recovery pula tiba-tiba. Hello, PowerPoint, come on. So a test charge is always positive and negligible. So how does the test charge feel about positive Q? So it will feel disgusted, right? And it will try to repel. So the direction is away from the positive charge. So here, okay, this is just a guideline for you. So if the test charge wants to move away from the source charge, which means that the electric field lines will follow this way, will go away from the charge. It wants to go away from the charge. Okay, so what about negative charge? Putting a small teeny weeny test charge over here, how does the test charge feel about negative Q? It is attracted. So it will go towards the negative charge, and the electric field lines should follow this. So the electric field lines should go into the negative charge. Okay, so that is a little trick to not have to memorize whether it's going in or out. Okay, but if it confuses you, then just use your own way on memorizing it. Alright, so remember that the equation for electric field is kq over r squared. If my q is bigger, which means that my electric field will be bigger. If my Q is small in value, my electric field will be small in values. This is the same case for the electric field lines. So the bigger the E, right? The bigger the E, the more electric field lines it will have. So for instance, look at this diagram. We have positive 1 coulomb for this charge. So it has 1, 2, 3, 4, 5, 6, 7. 7 lines. On the other hand, this charge is, the value is 2 coulomb. It will have 14 lines. It will have double the amount of lines compared to a charge that has a value of 1 coulomb. Is it necessarily 7? No, this is arbitrary. If the question draws 5 lines for 1 coulomb, that's fine. And they ask you, draw the electric field lines for a charge that is 3 coulomb. So you know that 1 coulomb has 5 lines, which means that for a 3 coulomb charge, it should have 15 lines. Okay? So the number of lines is arbitrary. You just need to know that the lines should be proportional to your value of charge. Okay, moving on. Rules for drawing the electric field lines. It must begin on positive charge. Because why? Remember, it will follow the direction acting on a test charge. The test charge feels disgusted. So the source wants to follow this line. So it will start from the positive charge. And if there is a negative charge, positive charge going towards, so it will want to go, the lines will be going towards the negative charge. So ultimately, the lines coming from the positive charge will end up at the negative charge. And this is how it looks like. Okay, so you have like 1, 2, 3, 4, 5, 6. Oh, I can't count. So an electric dipole that is consists of 2 equal and opposite charges will look like this. And this is an electric dipole consisting of 2 equal but like point charges. Tadi, positive and negative. This one is positive and positive. So the lines will not end up, if this is a negative, then the lines go into the negative charge, right? But since both are positive, the lines just move away from each other. Now, a rule to remember is that the lines should not ever overlap. The lines should not ever overlap with each other. And the denser your lines are, the greater your E, the greater your electric field. The further away the lines are, the smaller your E. Okay? So that is how it is. So positive go to negative. So the electric field lines come from the positive, ends up at the negative. A denser line means a stronger electric field. A less dense line tells you that the electric field is weak. Okay. So this is another example of electric dipole. So this is unequal. One is positive 2Q, one is minus Q. Let me calculate this again. So I start from here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 lines is not going into negative charge. 1, so it's 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 goes into the negative charge. So it's 8 plus 8, which is 16. So 16 lines come out from the positive 2Q. And the number of lines that should end up at the negative charge should be half of the number of lines from 2Q. So half of 16 is 8. So 8 lines go into minus Q. So 16 from 2Q, 8 into minus Q. Remember, the number of lines is proportional to the value of the charge. Okay? Okay, so now we go into electric flux. Electric flux given by this symbol, I forgot what it's called, is determined by the number of electric field lines, E, that pass through a cross-section area A. So the equation given by the equation for electric flux is EA cosine theta. EA, so this is electric field, this is area, or it's written over here. So the angle theta is between the direction of the electric field and the plane of the area A. Okay, so that's the equation. How do we determine what is the direction of A? So the direction of A is always perpendicular to the surface. Always perpendicular to the surface. What does perpendicular mean? Perpendicular means 90 degrees to the surface. So if I had a surface like this, or a surface like this, or a surface like this, my angle for the my direction for A is this way, and the direction for A is this way, and the direction of A for this guy is this way. Okay, so what happens if I have electric field going through these surfaces, right? So this is the line of my electric field, and then I have to decide what is the angle between E and A. The angle between E and A for this guy over here, number 1. Okay, the angle is, my A is going this way, my E is also going this way. The angle between them is a 0, which means that my cosine 0 is equal to 1. Okay, so angle is 0 degrees. What about this guy? So this is the angle of my A, this is the angle of my E. The theta should be between them, like this. Okay, and this is the direction of my A. The direction of my E is this way. So this is the angle of the angle for my equation. Okay, so the angle between them is 0. This is the angle and this is the angle. Always between the A and the E. The A and the E. Okay. Now Gauss Law states that for any closed surface enclosing a total charge of Qn, the net electric flux through the surface is given by this equation. So electric flux, the net electric flux is Qn, which is the charge enclosed by the surface, and epsilon naught is just a constant. Let's see this diagram. So this is our imaginary surface. It looks like a ball, and I want to know what is the flux through this surface. What is the electric field lines through this surface? So we have like 1, 2, 3, 4, 5, 6, 7 charges, which gives us a negative Qn, right? So my Qn is negative 7Q. So we know that a negative charge, the field lines will go into the negative charge, which means that my electric field lines will go into the surface, and the number of field lines, the field lines that go through a surface perpendicularly, is known as the flux, electric flux. So we are looking at electric flux over here. Previously, what is the difference between the previous example? So the previous example is for an open surface, which means that if there are electric fields, it will go through the surface, but it is not enclosed. It's not enclosed. So this is my E. Wait. Let's say our E is this way. Okay. So I can see that there are 3 electric field lines going through my surface. But to calculate for the flux, I need to know the angle between the electric field and the area. So area is always perpendicular to the surface, so this is the angle right? So this angle and this angle and this angle should be the same. Okay, so that is for an open area. This is for an enclosed surface. So I want to know what are the electric field lines going through this surface, and it is given by Q in over epsilon naught. It is perpendicular, so electric flux is proportional to Q in. So the bigger your Q in is, the more charges that you have inside your surface, the bigger the electric flux. Okay? Okay, so we have an example. What is the electric flux? Electric flux given by this symbol, passing through a Gaussian surface that surrounds a 75 millicoulomb point charge. So I have charge that is 75 millicoulomb and it is positive, and I have a Gaussian surface that surrounds this charge. So my surface is given by this orange line. Okay, so I want to know what is the electric flux going through, what is the electric flux of this surface, right? Okay, so now I try to figure out whether my electric flux is going outwards or going inwards. I have a positive charge. Remember, positive, the electric field lines go away from the charge, which means that my electric field lines would look like this. So this is the electric flux that I am expecting, right? And the electric flux should be perpendicular to the surface. Okay, it's like that. Okay, so given Q in as 75 times 10 to the minus 3 coulomb, my electric flux can be calculated using this equation. Epsilon naught is given as 8.85 times 10 to the minus 12 coulomb squared over Newton over meter squared. Okay, so C is cancelled out with C. So I'm left with, this guy goes up here, this guy goes up here. So I'm left with Newton meter squared over coulomb.